Hi, my name is Chris Masterjohn. I have a PhD in nutritional sciences, and today I'm going to be explaining why ketogenesis is not all about carbs and insulin, alternatively titled, How to Eat a Ketogenic Diet Based on Pasta. In order to understand what the true biochemical event that initiates ketogenesis is, it's important to just generally provide an overview of how we burn energy in general. If we imagine that we are burning carbohydrate for energy, what we will do is we will break glucose in half and slightly oxidize it during glycolysis to produce pyruvate. That pyruvate will enter the mitochondrion and it will be further oxidized to produce a 2-carbon unit called an acetyl group. That acetyl group will be carried by CoA in the form of acetyl-CoA into the TCA cycle, which is where we break the carbons apart and release them as carbon dioxide in order to harvest the chemical energy in their chemical bonds as high energy electrons and hydrogen ions that are carried to the electron transport chain, where the energy within is used to synthesize ATP, the general energy currency of the cell. And the key event that allows the acetyl group to enter the TCA cycle is that it condenses with a compound known as oxaloacetate, or OAA, in order to form citrate. And citrate is the compound after which the cycle is named. This is called the citric acid cycle, or because citrate has 3 carboxyl groups, the tricarboxylic acid, or TCA cycle. Now, this event of OAA condensing with the acetyl group to form citrate is not only the key event that normally allows the acetyl group to enter the TCA cycle and be burned for energy, but it's also the key event that we need to understand in order to understand why is it that ketones form. Before moving on to ketones, we need to understand why it's sometimes important to replete the OAA. We call this a cycle because OAA joins to the acetyl group to form citrate, goes through a series of chemical reactions, and then we just come back to OAA, and it's free to repeat the cycle. And even though that's true, OAA fulfills other roles. So OAA, or any of its precursors, which are not shown here, leave the TCA cycle to synthesize certain amino acids. And if that's the case, that means that we need to, every time OAA or one of its precursors leaves the cycle, we need to put OAA back there. And usually the way we do that is to take pyruvate and turn it into OAA. And so normally if we're burning carbohydrate for energy, for the most part, pyruvate is generating acetyl-CoA, but some of that pyruvate is generating OAA. Because of this importance of using carbohydrate to supply OAA, we have a phrase in biochemistry known as fat burns in the flame of carbohydrate, or fat burns in a carbohydrate flame. And what that means is that if we're burning fat for energy, we do it in a process called beta-oxidation. That generates the acetyl group of acetyl-CoA, and that acetyl group, even though it's coming from fat, it needs OAA to enter the TCA cycle in the exact same way as any other acetyl group, no matter where it comes from. And because carbohydrate is normally the main way we get OAA, then OAA is the flame, TCA cycle is the fire, and fat burns in the flame of carbohydrate means these acetyl groups derived from fat need that OAA flame derived from carbohydrate to get into that fire. Now, it would be better to say that fat burns in the flame of OAA, because even though OAA and its precursors can leave to form certain amino acids, it's just as true that certain amino acids can form OAA or its precursors, and they can be the source of OAA. And what that means is that the true saying should be fat burns in the flame of carbohydrate when it supplies OAA, or of protein when it supplies OAA. Now, this has a practical implication because it means that if you don't have enough protein and you don't have enough carbohydrate, that OAA has to come from somewhere, and the only place you're going to be able to get it is your lean muscle mass. And that means that if protein and carbohydrate are restricted enough, you could lose lean muscle mass. And that also means that because fat generates acetyl groups, but fat cannot generate OAA, fat and ketones are unable to mitigate against that effect. That doesn't mean that fat, because it supplies calories, or ketones because they supply calories, can't spare lean muscle mass relative to hypocaloric conditions, but fat cannot supply OAA. And so if protein and carbohydrate are low enough, no matter how much fat you eat, it's not going to be able to spare the lean muscle mass that's going to be caused by making the OAA that allows you to burn that fat for energy. And when ketones come into this cycle, they enter as acetyl groups, and so you need that OAA from protein or carbohydrate even to burn ketones for energy. Now, under conditions of carbohydrate restriction, you not only do not have carbohydrates supplying the OAA, but that OAA is leaving the TCA cycle because it can be used to synthesize glucose in the process of gluconeogenesis. And when you restrict carbohydrate, that's exactly when you need to make new glucose. So whatever protein is generating OAA is being used for gluconeogenesis. And in general, OAA is becoming depleted. In the liver, that's the main site of gluconeogenesis. So although OAA could be depleted throughout the body, it's primarily in the liver where OAA is really going to take a hit. But at the same time, the liver is also the main site of beta-oxidation under these conditions. So fatty acids are being released from adipose tissue. If fat in the diet is high, then fat's coming in from the diet, and the liver is bearing the brunt of all of that fat flux. And so the liver is the main site where you're going to have disproportionate beta oxidation for the service of other tissues in the body. And that means that you're going to have this massive oversupply of acetyl groups and this massive undersupply of OAA, and that is the exact condition that leads to accumulation of acetyl groups as acetyl-CoA, and that accumulation is the biochemical event that initiates ketogenesis. In ketogenesis, we first form acetoacetate, which is essentially, although there's a more complicated enzymatic process behind this, that's essentially the condensation of two acetyl groups. And that can then be converted either to beta-hydroxybutyrate or to acetone. Acetone is what gives nail polish remover for the ladies or paint thinner for the dudes its characteristic smell, and it's also what gives someone on a ketogenic diet ketone breath, because acetone is very volatile and can be released in the breath. Beta-hydroxybutyrate is often measured in the blood as a marker of ketogenesis. Now, so far we haven't talked about insulin, and that's because insulin is not directly the thing that regulates ketogenesis. The thing that directly regulates ketogenesis is the oversupply of acetyl groups relative to OAA. However, insulin does have an important role to play here, but talking about insulin is also a good point to start talking about why MCT oil not only offers us a second practical implication to talk about, but also allows us to dissociate ketogenesis from insulin. So let's just first talk about insulin. Ordinarily, we have fat in the adipose tissue, and we may have fat in the diet, and that fat in the diet will make its way into the blood. Insulin will stimulate the uptake of triglycerides into adipose tissue from the blood and will prevent the release of free fatty acids into the blood from adipose tissue. And that means that insulin is taking fat from the diet and putting it in adipose tissue and is preventing us from burning our own stored energy by releasing it into the blood. Some people say this leads to obesity, but you have to keep in mind that insulin is also causing us to stimulate carbohydrate. So this effect doesn't cause us to decrease our energy expenditure. Instead, it causes us to shift our energy toward carbohydrate and away from fat in proportion to the amount of carbohydrate in the diet. Now, long chain fats and medium chain fats are treated differently. And when I'm talking about medium chain fats, I am going to exclude lauric acid, which is the predominant fatty acid in coconut. It's often called a medium chain fatty acid, but With respect to energy metabolism, in many key ways, it resembles a long-chain fat. So let's forget about lauric acid and just talk about long-chain fats and fatty acids with 10 or fewer carbons, which for our purposes we'll just call medium-chain fats. Those fatty acids are 15% of coconut, 100% of medium-chain triglyceride oil, or MCT oil, which is derived from coconut, and are 6% of, more or less, of butter's fatty acids. When you consume long-chain fats, they go from the intestines into chylomicrons through the lymph into the blood. The other tissues, such as adipose tissue, get first dibs on anything that's there, and whatever's left over is called chylomicron remnants, and those make their way into the liver. Medium-chain fats, by contrast, go through the portal vein from the intestines directly into the liver, and they thereby escape the effects of insulin in the blood. And so these are preferentially delivered to the liver, whereas long-chain fats, in the presence of carbohydrate that stimulates insulin, are preferentially delivered to everything else before they get to the liver. That means that long-chain fats can only make it mostly to the liver in the absence of carbohydrate, whereas medium-chain fats make it to the liver even when there is carbohydrate. And making it to the liver is one of the first events that's important to allow them to eventually become ketones. Once fatty acids are in the liver, they need to use the carnitine shuttle to get into the mitochondrion. Now, this is true only, again, of long-chain fats. So the fatty acid, which is shown as acyl-CoA here, is delivered by CoA to carnitine. Carnitine shuttles it across the membrane into the mitochondrion and delivers it back to CoA to form fatty acyl-CoA. Carnitine then goes to the other side of the membrane and just repeats this shuttling process over and over and over again. Well, long-chain fats need the carnitine shuttle. Medium-chain fats don't. They just go right into the mitochondrion. That's important because insulin indirectly suppresses the carnitine shuttle. What that means is that insulin suppresses the entry of long-chain fatty acids into the mitochondrion, and it does not suppress the entry of medium-chain fatty acids into the mitochondrion. And it is entry into the mitochondrion that allows them to be beta-oxidized, and beta-oxidation is a necessary first step to eventually enable ketogenesis. So if you stop and think about this for a second, what that means is that ordinarily we have to choose between burning carbohydrate for energy or fat for energy. And that's not an absolute choice, it's a proportional choice. But what that means is that if we get a certain amount of carbohydrate in the diet, in proportion to that amount, we will choose to burn it instead of an equivalent caloric load of fat. But because MCT oil or medium chain fatty acids in coconut or shorter fatty acids in butter, because they escape these effects of insulin, they allow us to burn carbohydrate and burn those fatty acids at the same time. And that is, I'll show you shortly, the reason why they have an independent ketogenic effect even in the presence of carbohydrate and insulin. So first of all, the study that I'm showing you here is a study wherein they took 12 healthy male college students of normal body weight, gave them 4 breakfasts on 4 different occasions separated by 1 week in random order. The breakfast consisted of 300 grams of pasta, 100 grams of tomato sauce, and roughly 40 grams of either olive oil, lard, or MCT oil, or a low-calorie fat substitute. And what you see on the left is their energy intake at lunch. Not shown here is that they also allowed these people to ask for lunch on their own. And the people who had MCT oil for breakfast, or I should say when the people had MCT oil for breakfast, they waited longer to ask for lunch. But then at lunch, they also ate fewer calories than all the other groups. And if we want to be generous, we'll compare them to the next best group, or the next best breakfast, I should say. And when people had MCT oil for breakfast, they ate 43 fewer calories at lunch. In order to understand why that might be the case, let's look at beta-hydroxybutyrate, a marker of ketogenesis. Before the breakfast, it was some non-zero but very low amount, and that reflects the fact that an overnight fast in and of itself is independently ketogenic. But then when they had this carbohydrate-loaded breakfast, that amount went even lower in most of the groups. But in most of the breakfast, I should say. But when people had MCT oil for breakfast, instead of going down, MCT oil went up. And it didn't just go up a little bit, it skyrocketed through the roof. Consider that compared to overnight fast, which is ketogenic in everyone, eating pasta when there's MCT oil on top of it is strongly ketogenic. Now, it's the MCT oil, not the pasta, that's ketogenic, but that same pasta, in the absence of MCT oil, suppresses the little bit of ketogenesis that you have from the overnight fast. So this is a remarkable, radical, fundamental difference from every other diet, and it occurs in the presence of a carbohydrate-loaded, pasta-based meal. Now, you can say, well, if I look at the graph, I only see 0.3 millimoles per liter. Is that skyrocketing? How does that compare to a ketogenic diet? The truth is, it depends what kind of ketogenic diet we're comparing it to. So I want to show you two ends of the spectrum so you can get a sense of the range. And in this first study, I want to show you what happens when you restrict carbohydrate content to 10%, eating 60% fat, and keeping protein around 30%. This has a ketogenic effect, but it's much lower than what you would get from the ketogenic diets that are used to treat epilepsy. If you look at this graph of beta-hydroxybutyrate, the triangles shown at the top are the very low carbohydrate diet. And you can see that that diet is ketogenic, but because the meal is 30% protein, 10% carbohydrate, which not only supplies a little bit of insulin, but more importantly supplies oxaloacetate, that meal is anti-ketogenic. And then their ketones rise back up to 0.2 millimoles per liter. Now, compared to the other diets, particularly with the low-fat diet, that diet is ketogenic. And so in fasting or after the meal, blood levels of ketones are a lot higher. But when we compare it to what you get with MCT oil plus pasta, it's less of a ketogenic effect. So that means that adding MCT oil to your pasta makes that pasta-based meal more ketogenic than restricting your carbohydrate to 10% of your calories. To show you the opposite end of the spectrum, this is a study comparing the classical ketogenic diet to the MCT oil supplemented ketogenic diet that's used to treat refractory epilepsy in children. Here you can see that at 3, 6, or 12 months on the diet, the beta-hydroxybutyrate was over 4 millimoles per liter on the classical diet and was somewhere around 3 millimoles per liter on the MCT oil-based diet, which includes potentially more protein and carbohydrate. And so you can see that these levels of beta-hydroxybutyrate are much higher than 0.3 millimoles per liter. And so MCT oil on top of pasta is not going to give you as much ketogenesis as these traditional, more extreme diets will, by any stretch of the imagination. But it does give you more ketogenesis than a modest ketogenic, very low carbohydrate diet does. One thing you have to keep in mind is that these diets are so strongly restricting carbohydrate and protein that we don't know the exact degree to which elevated blood levels of beta-hydroxybutyrate reflect the production of more ketones or reflect the absence of the ability to use those ketones because restricting carbohydrate and protein depletes oxaloacetate most pronouncedly in the liver where the ketones are made, but also in the other tissues that need the OAA to use those ketones. And certainly if the ketones are spilling out into the urine, then clearly some of them are not being used. But I think we really do have to ask the question, when you look at these blood levels, you can't just assume that it just reflects stronger ketogenesis. But I think pretty much everyone would agree that these are providing a lot more ketones than just putting MCT oil on top of pasta. So I want to conclude by noting two things. First of all these approaches to ketogenesis are clearly the same in some ways in that they increase ketones in the blood. But they're also fundamentally different in some ways. In the case of MCT oil, you are adding more energy. So you are simultaneously burning glucose and simultaneously burning fatty acids for fuel. And you're getting those ketones with the glucose and with the insulin. And so if we come back to the question of why did those people eat less at lunch? Why did they wait longer to eat lunch in the first place? I think it's because both glucose and ketones are reaching the brain, and the brain feels like there's so much energy that it will tell the body that there's not as much a need to eat. That's a model of supplying more abundance to the body. In carbohydrate restriction, that is a model of selective deprivation. You're not depriving yourself of food necessarily if you're eating the same calories, but you are depriving yourself of a certain particular nutrient and all the micronutrients that go along with carbohydrate-rich foods. But that carbohydrate itself plays important roles in the body, and you could potentially lose those. Whereas in the models of supplying ketones on top of everything else, you theoretically have the ability to reap the benefits of both. So I think you have to ask the question, if you're on a ketogenic diet, I'm not on one, but I think in general, if you are on one, you have to ask the question, why do I want the ketones? If I have a need specifically to restrict carbohydrate per se, then that approach makes a lot of sense. And if you're dealing with a neurological condition where you can't use carbohydrate effectively, then it makes sense to replace the carbohydrate with ketones. But if you're trying to get a modest ketogenesis so that you can get some cognitive enhancement from the ketones, or you can get some enhancement of certain types of athletic performance from the ketones, then you may want to ask the question, number one, is the approach I'm using working? If it's working fine, then why fix a broken thing? But on the other hand, if you are getting those benefits, but you're losing other benefits of carbohydrate, like supporting the antioxidant system or supporting sex hormones and thyroid hormone, or relying less on adrenal hormones, or supporting other types of athletic performance, then you may want to ask the question, do I need to restrict carbohydrate to get those ketones? Because I may actually be able to get even more ketones and use them more effectively by adding MCTs to the diet instead of restricting carbohydrate. And you could say the same thing for using exogenous ketones. That is a model of supplying more abundance instead of depriving the body of a nutrient. And so, yes, the arrival point of ketones is the same between these models, but how we get there is different. And that also means that those different routes, because they're fundamentally different models, whether you're restricting something or supplying something, they're going to have certain sets of health effects that differ between them. And so being able to understand the biochemistry and understand how these approaches differ allows us to better fine-tune our approach to what our actual values and priorities are. All right, so that's it. I hope you enjoyed this. If you want to share this as a YouTube video or a Facebook video, you can just share it in whatever way you're watching it. But if you want to share it as a downloadable or streamable podcast, or listen to it again on the go as a podcast, you can go to chrismasterjohnphd.com/22. That is also where you can find all of the show notes, which includes relevant links to the types of things that we were talking about here and sources for further reading. And eventually, when it's ready, that will also be where you can find the transcript of the podcast version of this discussion. All right, I had a lot of fun producing this video. I hope you either found it valuable, fun, or both. And signing off now, this is Chris Masterjohn, PhD of chrismasterjohnphd.com, and I will see you in the next video.